I have my primary, and I have my secondary. And remember, if you put an iron core in it, you get a stronger field, right? So they put an iron core in. That is shaped like that, okay? The reason is, what do the lines of B field do once they leave the solenoid? Right? They go into that dipole motion, right? So this is kind of just matching that dipole motion, but because the dipoles inside the magnet turn with the field, they also strengthen the field along the iron, right? So the iron actually kind of takes that natural path and then makes it even stronger, so that fewer of the lines leave, right? And so I end up getting lines of B field that go around like that and are stronger than they would have been otherwise, right? But if it was a solid piece of iron, right, again, I'd have an oscillating B field through here. So I would get eddy currents going perpendicular to the B field all through the thing. And it would heat up. And early transformers had a habit of like getting too hot and blowing up. Right? If it's cold on the outside, hot on the inside, there's thermal stress. So what they started doing was, let's see, the current's trying to go like that. They would cut the iron into a thin sheet, separated with a insulator. That stops the current from flowing over there. And then they do the same thing here. The current's trying to go like this. So if they laminate it like that, then they stop the currents, they stop all the thermal stress. Right? So that's why the thing is done that way, and that's the other part. Okay. All right, so now we're done with that part. Let's go to the last one. Oh, and I guess I should say, I found this, I went and bought it. This is an old survivalist light bulb, flashlight. They work really well with LEDs because they don't need much energy. This one's incandescent. But the idea is here on the inside, going back and forth, that's a bar magnet, solenoid. By the way, these are easy to make at home too if you want to. And so if I just do that, I produce some current and the light bulb lights, but again, because it's incandescent, you have to really shake it for quite a while to store up any energy in it, like a capacitor. Okay? But since it's there, I figured we can do that. Okay, this is the last one. I don't have a model generator. That's on my file. This is a model motor. It's meant to be DC on one side, AC on the other side. Haven't been able to get a good connection with the AC motor, so we'll just have to pretend, okay? Mm-hmm. But I've managed to get the DC working. And here's kind of the idea. DC power source, current comes through, and that's just not working. Hand me the screwdriver. And it's off, good, okay. It's hard to use a screwdriver close to magnets. All right. Okay, so current comes in, gets to the metal post, goes through the post, hits this guy, which misleadingly is called a brush. Okay, right? Because it brushes against the piece of metal there. Right, so that part is all connected conductor. And notice that little metal sleeve only goes part way around. Right, so when the thing is at this orientation, it's going into that piece of metal, and then it's hooked through a wire that goes into the solenoid, right? And the solenoid has a laminated core. Then it comes out the other wire, goes through the other brush, and then back out to ground. Okay, so you have a complete circuit. Okay, this two little sections of a sleeve on the thing that are metal, that's called a split ring, which makes sense. Commutator. You guys know what commutators are? Okay. If you commute every day, you are a commutator. You go one way in the morning and another way in the afternoon. Okay? That's what it means. It's just you do it twice in different directions. Okay? It's also a mathematical operation, but even in mathematics, that's all it means. Okay? So what it does is it says, okay, notice right here when I'm at what the equilibrium position would be, because here are the two magnets. Right, so here it's just going straight through. That's the equilibrium position for a coil. Okay, it's not making any connection at all. Right, if I started off a little bit, let's say this is the North Pole. This is hooked up so that that becomes the North Pole of the solenoid. Right, and this is the South Pole, and here's the South Pole. So the two South Poles repel, the two North Poles repel, and the north and souths attract, and it swings over here, right? It gets to this place, the new equilibrium place. Again, no contact here, but it has some velocity. So it keeps sailing through. Now it's making contact on the other side of the commutator. So once again, this has become a North Pole, and this has become a South Pole, and it keeps swinging, right? And the more current that I try and feed into it, right, the more torque, because the magnetic dipole moment's N times I times A, right? So the more current, it's going to try and go faster, right? And with a little bit of luck, it splatters current sometimes. So you two might want to be it splatters oil. Okay. As I discovered, right? Okay, so let's see if we can get. It does tend to be directional too. Oh, thanks. Okay. Almost did it, but then it knocked over. There we go. Making. All right, let's try it again. Let's go get some oil.
I'm half asleep.
Did you not sleep?
I didn't sleep and I just drink coffee when I'm so tired.
Oh.
Oh, gosh. Oh, you're up. Yeah. Oh, yeah, thank you. Yeah, I figured it was safe back there, so. Okay. It's just, this one looks younger than the 80s, but it had a lot of dust, and I don't think it's been used often. So all of the oil seems to have congealed about it. So that's why I said be careful, it'll toss some oil. All right, so let's turn everything on again. Oh, it's on the. Ah, come on, right other direction. I at least got it to work each of the last times. It is making electrical contact, it is burning oil. Oh, come on, come on.
So close.
Should be able to get up around 3 amps. So it's not making great contact. Okay, again, a little more oil. It's just got too much friction.
Oh.
It's usually what I travel with.
So you're, if you get like one time I forgot to like
Yeah.
10 to the 3, like times 10 to the 4.
We'll
It's the
change
ones
that
that are
around.
like in your suitcase.
Okay, let's try it again now.
There
There we go. Okay, so notice the trail of oil. Okay. But we finally got it to work. And the basic idea is if I lower the current, I lower the speed, increase the current, and I increase the speed. Okay? But notice it goes to a constant value of the speed until it loses enough oil and starts seizing up again. Right? It's actually nice watching the smoke come out. Okay, let's go through the, so we've gone through the mechanics of the operation. Let's go through what the voltage is doing, right? So first off, notice it's torque that's driving it, right? Because the solenoid becomes a bar magnet, and that means the dipole moment is sticking out of the North Pole. And in the B field between those two things, you feel a torque. Okay? So the power source, right, is giving the current to create the bar magnet and take advantage of the torque. Okay. So if I did some of the voltages on this loop, right, I'd have the power source. This obviously has some resistance, both mechanical and electrical. Okay, otherwise it wouldn't get hot. So I'm going to have an IR. Any other voltages?
Yes.
Hmm?
Yes.
Yes? Care
The
to make a guess?
the induced EMF, I guess.
Yes, the induced EMF. 'Cause from two sources, right? One is I have rotating loops in a magnetic field, right? So at the speed that it
I'm still on.
I thought I pushed that. Okay. Okay, so obviously electricity is not as dangerous as you would tend to think, because otherwise I'd be dead. All right. Okay, so when it's like this, all of the flux is going through the solenoid. When it's like that, none of it is, right? So I have a changing flux, and the rate of change is matching the rotational speed, right? So as it rotates faster from the torque, I also lose more voltage because the induced EMF is opposing the change. Here I'm putting through the voltage, right? That's the original thing that's causing the change as it goes through the commutator. So the induced EMF there is always going to be opposite that. So the induced EMF in a motor is called back EMF because it goes opposite the driving EMF. Okay? And then the other thing is I'm switching the direction of the current inside the solenoid. right? So that switches its own interior B field twice every rotation, right? So I'm going to get an induced EMF from that too, right? But it's also going to be at exactly the same rate as the other one, and it's also going to be opposite the change, so in the same direction as the other one. So you have two sources of induced EMF, both of them reducing the effectiveness of your motor, right? So you've got one thing that increases with the torque increases with it, so that increases the rotation rate, but as it goes faster, the induced EMF also increases, and that takes away from the driving voltage and takes away from the current. So you get a balance somewhere, right? So the thing to remember there is in a DC motor, you have voltage from the power source, IR from the loops, and then a back EMF, right? And that's your complete circuit. And that sets your rotational speed, okay? So over here you have to imagine, because we've gotten an electrical connection, but we haven't gotten it to turn. This guy would be the AC motor. Same basic operation, as you can tell, it's the same motor, right? The only thing is, if you look at that, the connections are made from two brass rings that are right there. Neither of them are split. So one of them is always the input, one of them is always the output. So what switches the direction of the little bar magnet here? Let's see, this is a DC motor. This would be an AC motor. What switches in the AC motor?
Your current.
Oh,
Yeah, the current switching, but this time because of the power company. Right? You're not doing anything to switch it around. Okay, so here you switched your north and south poles at the rate you were rotating. On those connections, you're switching them 60 times per second. Right, so an AC motor hooked up to line voltage operates at what frequency? 60 hertz. Okay, and you don't get it to go faster or slower. Okay, but that's basically the only difference. Right, so the one thing that's missing is the split ring commutator, and you'll still have the input voltage, you'll still have the IR, you'll still have the back EMF. Okay, why would you want an AC motor if you can't make it go faster?
so you can rely on the constant.
Yeah, obviously Tesla does not want AC motors. Okay, right, because they want the motor to turn faster, but what?
Maybe in some application you'd want a constant.
Yeah, how about an electric clock?
Oh, there you go. Yeah.
Right? So before we had these little silicon crystals, right, we had geared electrical clocks. And it was nice for the motor to turn 60 times per second because it was an easy thing to gear another factor of 60, you know, from the seconds to the minutes and from the minutes to the hour. Right? And so that 60 cycle per second was put in simply because as soon as we started doing electric, doesn't sound like the right word, electricalization?
Electrification.
Electrifying.
Oh.
There we go. As soon as we started electrifying America, which that doesn't sound right either. Okay. Electrification. That's the word. Okay. As soon as we started the electrification process, which remember began around the turn of the century under Tesla, right? Before that, it was little mom and pop shops. But when we started doing that, Franklin Roosevelt looked at that and said, okay, just like Michael Faraday said when he was talking to the Queen, we can produce electricity where it's cheap, like the Columbia River Valley and the Tennessee Valley, right? Both of which are lined with dams and stuff like that. Hoover Dam, right? All of the things like that. We can produce wholesale electricity cheaply and then send it anywhere we want to in the country at high voltage. So wouldn't it be nice if all of these places that are in abject poverty started getting factories, right, that are electrically powered? Okay, so his idea was to get out of the Depression and create jobs by the electrification of America. Right? And by and large, it worked. It took some time. The flip side of that was that you had to train a rural society to show up for work on time. Okay, and kind of get the feel of it. If they didn't have electrical clocks, a good timepiece made with springs is a piece of workmanship that is expensive. So most people didn't have watches. So well into the 1930s, people didn't say, hey, I'll meet you at 11:30 and expect you to be on time. They said, oh, I'll meet you around noon, right? Or come in bright and early in the morning, come in mid-morning, right? The time slot was like that, right? And only the wealthy tended to have watches, and the wealthy weren't showing up for jobs at factories. Okay, so the 60 cycle per second was done so that they could make cheap clocks and then train people to be on time. Right, and that literally is the way it happened. Which means if you grew up in like rural Oklahoma, like I did, you're not concerned with time. Okay. Anyway, that's kind of the last piece of it, right, and the last story that I have to go with it. Any questions on a motor? Oh, okay. If it's a generator, I just unhook this, right, and I rotate the loop, and I just look for the induced EMF, right? And the induced EMF would produce a current coming out. If it has a split ring commutator, then it produces a DC current, right? If it doesn't have a split ring commutator, since I'm increasing flux, then decreasing flux, right, it gives me an AC current. Cool. It's okay? Right, so that's the lab for today. Do me, I'll come in probably over the weekend and start cleaning things up.